So recursion is a very interesting method, and this exists in multiple languages, not necessarily only in Python. So recursion basically means calling a function within a function. So in a nutshell, that's what it is. But let's understand why it's needed. So for those of you who don't know what a factorial is, factorial of a number. So let's say if I say factorial of 5, what it means is you multiply 5 with 4, with 3, with 2, and with 1. Okay, whatever value you get here is called the factorial of 5. Factorial of 5 is 120. Okay, but one fun thing here is factorial of any number n. So for example, factorial of 5 can be written as 5 multiplied by factorial of 4. But because what is factorial of 4? Factorial of 4 is multiplication of 4 with 3, 2, 1. And what is factorial of 5? Multiply the factorial of 4 with 5 and you get factorial of 5. Right? So in a nutshell, factorial of any number n, of any positive number n, is nothing but n multiplied by factorial of n minus 1. Here the fun part is the factorial of 1 is 1 itself. Right? When you're writing something like this, okay, here you have to remember that factorial of 1 is 1 itself. So when you have these two conditions, now what is factorial of 2? 2 into factorial of 1. 0 is neither positive nor negative, so we'll not talk about factorial of 0. Actually, factorial of 0 is 1, but let's not talk about it right now. It's not useful. For our case, it's not useful. Okay, so when you have these two, so this is called a recursive statement, or this is called recursion, where I'm computing the value of a function using some operation and the value of the same function on a slightly different number. See, here factorial is computed using the factorial. And this is called the limiting case or the boundary case. This is called the boundary case, where I'm saying the factorial of 1 is 1 itself. Right? So when you have functions like this, we'll see one more function called Fibonacci a little later. It's also pronounced as Fibonacci. Okay, so we'll come to the function Fibonacci a little later, but let's look at factorial. This is simple, right? Now, how do you implement functions like this? Such functions occur a lot in mathematics, and they occur a lot in, if you've studied data structures, they occur a lot in data structures and algorithms. If you can represent a function as itself with a slightly changed parameters or arguments, it's extremely useful. We'll see an example. Okay, so imagine let's implement factorial. It's not very hard, right? Here is my function definition. It's very elegant. See, what I'm saying here is factorial of number, return 1 if num equals to 1. Okay, what does this mean? This means I'm saying that factorial of 1 equals to 1, else return num multiplied by factorial into num minus 1. So what am I saying here? Factorial of n is nothing but n multiplied by factorial of n minus 1. This is the definition of factorial, right? I'm just using the definition of factorial itself. And what I've done is, this is literally one line of code. This whole thing is one line of code. Of course, I could have computed factorial using a for loop, but recursion makes it much more elegant, because this is how I think of factorials. This is the recursive definition of a factorial. There is a non-recursive definition of a factorial, which is factorial of n equals to n into n minus 1 into n minus 2 into so on and so forth up to 1. This is a non-recursive definition. This is a non-recursive definition. I'm using the recursive definition to be able to compute factorials very elegantly. Now, the way I call it is very simple. I just say num5, right? And I just say factorial of num. Now, let's understand what's happening internally. Okay, this is very important. What happens when you call this function? The flow of the function, the flow of the program is very important. Okay, let's understand. So when I call factorial of 5, so here I'm calling factorial of 5. So I'm calling factorial of 5. Okay, when I call this, what happens? It goes here, It says return 1 if num equals to 1. No. So it says return num multiplied by factorial of num minus 1. To produce this product, to compute this multiplication, it now has to compute factorial of num minus 1. So now it calls again the function factorial with a value of num minus 1, which is 4. Right? Now when it calls factorial of 4, now it goes back again here. Now it says, oh, return 1 if num equals to 1. It's not. Right? So what is it doing here? To compute factorial of 5, it called factorial of 4. But here again, it will try to multiply 4 with factorial of 3. It will keep calling this. It will now call factorial of 3, which will call factorial of 2, which will call factorial of 1. So it will keep calling this recursively. This is the recursion part. So when it calls factorial of 1, now it goes in here and it says return 1 if num equals to 1. So it will return 1. When this returns 1 here, at factorial of 2, I was supposed to do 2 into factorial of 1. So what it does is it does now 2 into 1, which becomes 2. So this function now returns 2 here. Now this 2 will be multiplied by 3 because see, look at this here. I have num multiplied by factorial of num minus 1. So 2 into 3 becomes 6. So this function now returns 6 here. Now this 6 will be multiplied by 4 and I get 24 here. And this 24 will be multiplied by 5 and I get 120 here. This is how the function flow happens. Okay, it's basically like I'm going into the lower values of factorial and I'm coming back. So this is called the function call stack. Okay, you can think of it like a heap, like a stack of things, right? Heap has a different meaning in data structure, so I'm not using that. This is a stack of function calls, right? Because if you look at it, I'm starting with factorial of 5 and I'm going down the pile. As I go down the pile here, right? As I go down the pile here, or the stack. So I go down the stack and then I come up the stack. Okay, this is how internally recursion works. Okay, now the good part is, what are the advantages and disadvantages of recursion? The biggest advantage is it makes the code look clean and elegant instead of writing for loops. If you have a complex task that can be broken down, if there is a recursive definition, for any operation you're doing, for example, for factorial, there is both a recursive and a non-recursive definition. If a recursive definition exists, it makes code much more elegant, simple to implement. The biggest disadvantage is it is hard to follow because it's not like a simple for loop or a if-else condition. Sometimes it becomes inefficient because of the stack that we saw, because you're calling a function within a function within a function. And when you call a function, there is some overhead. There is some memory and time that are used, more than normal cases. Okay, so it is slightly inefficient. The worst part about recursion is if you have a bug in your code, if you've done some mistake, it's extremely hard to debug. Because unlike regular code, which you flow like step by step, right, or iteratively, right, in a for loop, recursion is calling the function within the function. It's slightly more tricky for us to typically think in recursive fashion. And hence, if you have introduced a bug, if you have written some mistake in your code, debugging it can become fairly hard. Okay, so since we have understood, we have to be careful when we implement recursion, just slightly careful. Okay, now let's look at a very interesting code. So for something called as a Fibonacci sequence. And what is a Fibonacci sequence? Let me explain that. The Fibonacci okay, let me show you. Fibonacci of 0 is 0. Fibonacci of 1 is 1. 2 is basically sum of these two numbers. Okay, now for 3, okay, for 3, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we can just, I can call this the 0th number or the first number, it really doesn't matter. Okay, so but the essence is this. Okay, so let's say you might call this the first number, the second number, the third number in the Fibonacci sequence, 5th number, 6th number, 7th, 8th, 9th, and 10th. So any number in the Fibonacci sequence is the sum of the previous two numbers. Pick any number, pick this number. This is the sum of the previous two numbers. So if you sum 13 with 21, you get 34. So Fibonacci of any number n is Fibonacci of n minus 1 plus Fibonacci of n minus 2. Okay, this is the recursion. This is the it's called the recursive equation, because you are defining a function with using itself with slightly different arguments. Now for every recursive equation, you also need to have the boundary case. Okay, so let's look at the boundary case of recursion. Boundary case has been called multiple different terms by other people. Here, let's just call it boundary term. So I am saying Fibonacci of 2 equals to 1 and Fibonacci of 1 equals to 0. Because if I don't have these first two values, I can't compute the third value, right? So my boundary case basically has two statements, that Fibonacci of 2 equals to 1 and Fibonacci of 1 equals to 0. Now we can implement this using recursion very easily. Look at what I'm saying. Return num if num is less than equal to 1. Okay, so here in this code, what we're doing here is, or else let me just call it num less than equal to 2. Okay, so Fibonacci of 2, Fibonacci of 1 and 2 is this, right? So now let's see what happens when I execute this code. Okay, okay, there's a small error here. This is a problem with Python 2 and Python 3. Those of us who are used to Python 2 do not put parentheses after for print, right? So now let's rerun this. Now you're getting the same value, right? So what I'm saying here is that if you're given Fibonacci of 1, I'm saying Fibonacci of 1 equals to 1 itself. Fibonacci of 2 equals to, oh, there is a small bug. Sorry. Okay, let me just say num less than equal to 1. So this is the right implementation. Now let me explain you why. Okay, so what it's saying here is return num if num is less than equal to 1. Okay, so let's see. So what I'm saying here is Fibonacci of 0 equals to 0, Fibonacci of 1 equals to 1. These are my boundary cases. Okay, and my recursive case is Fibonacci of n equals to Fibonacci of n, Fibonacci of, okay, let me just erase this small error here, but we'll correct it, is Fibonacci of n minus 1 plus Fibonacci of n minus 2. Okay, so imagine if these were my conditions. That's how the code is written. Okay, if num is less than equal to 1, if num equals to 1, return 1. If num equals to 0, return 0. That's what I'm saying here. I have my boundary cases here. I have my boundary cases there, right? And this is my recursive case. This recursive case is here. Okay, so if you forget your boundary case, your program will continue to run forever. So these are your boundary case. And this is your recursive function. That's all there is. You don't have to worry about anything else. So for Fibonacci sequence here, right, all I have to say is print whatever terms I want. I can print all the Fibonacci terms here. Now it has been much easier. See, I've written the whole Fibonacci function, to get any Fibonacci number, I've written it in literally one line of code. Imagine, of course, I could have implemented this in a for loop or a while loop. It would have taken much more code. This is much more elegant because this is how I think of Fibonacci sequences. That any number is a sum of the previous two numbers. Right? That's how I imagine Fibonacci when I learn about it. Right? So, but remember, please don't forget your boundary case. If you forget your boundary case, the function will keep running. So the most important things to remember about recursion is always write your boundary case properly and don't skip it, and write your recursive equation. And always remember, recursion is hard to debug. If you do mistakes, you will get caught up in it. And it's very, very hard to debug, relatively speaking, as compared to simple for loops or while loops or if-else conditions. Okay, if you have these two, you can write your recursion. And recursion is extremely useful. If you have studied data structures and algorithms, you would have seen recursion everywhere. It's one of the most powerful ideas in programming across languages. And by the way, recursion, as I told you earlier, is not unique to Python. It's there in every major programming language we can imagine.